Hello everyone, and welcome to the theory prep video. Today we're going to be talking about directed graphs, and we'll also use this as an opportunity to discuss data structures, which is something that we haven't talked about in this course yet. So the first thing is, what is a directed graph? Well, as we talked about motivating graph problems, they often can model like networks, where you have a bunch of nodes and you have connections between them. But let's say we're trying to model like web pages on the internet, and we want the edges to represent links going from one page to another. Well, it's possible that one page might link to a second page, but not vice versa. And so we want to represent that with a direction in the network, right? Let's label these nodes A, B, C, and D. And it might be that B has this link to page C, but C doesn't link back to page B. And so we want to be able to capture this relationship with directions in our graph. And that's what motivates a directed graph. Another possible application of this would be in ordering. So sometimes when you have like software and you're trying to make updates, you might have to update like certain packages or certain systems before other ones. There are dependencies. And so you can represent that something is dependent on a different package by drawing an edge between those things. And then you can use directed graphs to figure out, which packages you should be installing first and stuff like that. So having motivated the definition, let's now define it. And you'll see that the definition is pretty similar to that of an undirected graph. So a directed graph is a set V of vertices and a set E of edges. And the edges are pairs of vertices that are not equal to each other. And the main difference between this and an undirected graph is in an undirected graph, the edges are sets, whereas here they're tuples. And that's because a set UV is equal to the set VU. It doesn't care about the order of the elements. Whereas a tuple, UV, is not equal to the tuple VU. And that captures the fact that an edge BD is not the same thing as an edge DB. Great. So now let's talk about the other thing that we're going to talk about today, which is a data structure. And before we sort of get into that, let's look at how mathematically we would write down this object, and then that might help us think about how we'll write it down in code. So mathematically, this graph on the left-hand side here, we'd write first as a set of vertices, and the vertices are A, B, C, and D. And then we'd have a set of edges, and the edges are A to B, B to D, D to C, and D to A. And so this suggests maybe one way of representing a graph, which is that we'll just make a list of vertices, and then we'll just make a list of all those edges. And that would be a perfectly fine way to represent a graph. But whenever you're thinking about how should we represent something in code, what data structure should we use, you should be thinking about like what graphs are we commonly going to represent and what operations are we going to need to do on them a lot. And for example, a operation, if we think back to the website example that we might want to do is, we're looking at some website B and we want to know, how many websites does it link to, or like, does it link to this other website? Those would probably be pretty common questions that we're asking. We want our data structure to be able to efficiently support those queries, which is to say, answer those really quickly. The issue here is that in order to answer the question, what pages does B link to, you got to look through all the edges, right? Because you've just listed them out in a big list, and that will take a long time. So that motivates a little bit more efficient definitions. It turns out the two common ways that we talk about representing graphs are called adjacency lists and adjacency matrices, and they'll do this operation of looking up outgoing edges much faster. So let's present the adjacency list first. In the adjacency list, you have a list of lists, and you have one sublist for each vertex in the original graph. And the elements of that sublist are just all of the outgoing neighbors of that vertex. So for concreteness here, in this first list here represents 0 in the graph, and we put a 1 there because there's an edge from 0 to 1. Similarly, this represents 1, and there's an edge from 1 to 2, so we put a 2 there. The third list represents 2, and there's 2 outgoing edges from 2, going to 0 and 3 respectively, so we put 0 and 3 here, and 3 has no outgoing neighbors, so we don't put anything there. And one thing to note is that in adjacency lists, we consider these lists as unordered, so this, you could just write 3, 0 here if you want as well. And let's present the other sort of way we could represent it. The other method is called an adjacency matrix. And if we have n vertices, an adjacency matrix will be n by n. And the adjacency matrix will have its ith j entry equal to, this notation, when we put 1 and then a parenthesized expression, means evaluate the thing in parentheses. If it's true, put a 1, otherwise put a 0. So this will be true if there's an edge in the graph going from I to j. And so you can see here, there's an edge going from 0 to 1. That's why we have this one. There's an edge going from 1 to 2. That's why we have this one. And then the two edges going from 2 to 0 and 3 respectively are for these two ones. And everything else is 0, right, because there are no more edges. So this would evaluate to z in those cases. Great, so those are two ways to represent the graphs. And you can see in both of these cases, if we want to know, again, taking the web page example, what pages page 1 links to, well, that's pretty easy. In the adjacency list, we just look up that list, and then that gives us the things it links to. In the adjacency matrix, we can look at this list and look for ones here. And so these are sort of better data structures than our first naive data structure where we just list out all the edges together. Because if you think about what will you want to be doing with graphs and the code representing graphs, you want to make sure that operations that you'll be doing a lot are really fast. So there are always pros and cons to data structures, and often in a data structure course, that's one of the things that you'll talk about. You'll talk about which scenarios is this data structure better for, which scenario is that data structure better for, and the answer is usually like it depends, right? So adjacency lists, if the graph is really sparse, which is to say it doesn't have a lot of edges. So for example here, if we're including self loops, there are 16 possible edges in this graph, but it only has 4. So it's relatively sparse because it doesn't have that many edges compared to how many it could have. Then our adjacency list will be a lot smaller than an adjacency matrix, right? An adjacency matrix always takes up n by n space. And then an adjacency list can take up a lot less if it's sparse. And another benefit, though, to adjacency matrix is that lookup time can be a lot faster. If you're asking the question, does there exist a link from 1 to 2? Well, in adjacency matrix, that's really fast, right? You just look up A, 1, 2, and you'll get either a 0 or a 1. But in an adjacency list, you got to go to the first list, and especially if the graph is not sparse, if there are a lot of outgoing edges, then you have to look through a bunch of those naively to get the answer there. So it's a little bit slower in that case. So you can see, depending on 1, the actual graph you're representing, is it sparse or not sparse? And 2, the operations that you're trying to do, you might prefer one data structure to another, but it really depends on both of those things a lot of times. And we'll spend the rest of this video giving an interesting property, but this property will result from using the adjacency matrix representation. So that's pretty different from what we've been doing in the course, because so far in the course, we've proved interesting properties about algebraic structures, right? About objects, mathematical objects. But now we're saying, if we code this object this specific way, then we get this cool property. So really it is diving more into the actual study of data structures. So let's take a motivating example here. And again, talking about the website example, we might be wondering, how many ways are there to get from page A to page B in at most n clicks? That's a little bit of a complicated question. So we'll just ask, how many ways can I get from page A to page B in exactly n clicks? And if we can answer that, well, then we can answer the at most n question because we could just add it up. So it's sort of sufficient to answer this question. Well, the theorem that we're about to prove says that if we have some graph G and we assume an adjacency matrix representation A, then if we just take A to the kth power and then look at the UV entry, that gives the number of k-length walks from U to V. And I think this is sort of a surprising result initially because it seems like a hard problem to solve. How many ways are there to get from this page to that page in exactly k steps? You got to try, all the neighbors and then go through those. And that seems like it might take a really long time. But actually, this just reduces that problem to just, squaring or cubing a matrix, which is something that we have algorithms for, and also is just like a much simpler process conceptually than trying to follow all those paths together. And so I want to just give a quick intuitive definition for walks. That'll be defined in the reading formally, but you can think of a k-length walk as a series of k plus 1 vertices that go from U to V, and every consecutive set of vertices must be an edge in the graph. So in other words, if we go back to our graph, a walk would be like 0, 1, 2, and that represents going from 0 to 1 to 2, just walking along the graph. The reason a k-length walk so this would be a 2-length walk, and the reason it would be a 2-length walk is because we are only walking on 2 edges, but that requires 3 vertices. So you can think of a walk as just, like a path going from from U to V, but traveling on the edges of the graph. Great. And so we're going to prove this inductively. The base case is that K equals 0. And A to the 0 is just the identity matrix, right? You take any matrix to the 0, and by convention, we say that that's the identity matrix. And we'll see that this actually does summarize all the zero-length walks from U to V, right? If U and V are different, then there's no way to get from one to the other in 0 walks and crossing 0 edges. And if we're on the diagonal, then U and V are the same thing. So this is just saying there's one way to get from a point to itself in 0 moves, which is just to stay there. So that makes sense. And now we will do the inductive step. So in the inductive step, remember, first we assume the inductive hypothesis. So we assume that A to the K, if you take the UV entry of it, gives the number of K-length walks from U to V. And we want to show this for K plus 1. So let's think about, for an arbitrary U and arbitrary V, how can we get from U to V in K plus 1 moves? Well, first we have to get from U to I in K moves, and then we have to get from I to V in 1 move, where I is just some arbitrary vertex, right? Because every K plus 1 path from U to V will first go down K edges and get to some intermediary vertex, and then go 1 edge and get to V. And if there are like 3 ways to get from U to I in K moves, and there's 1 way to get from I to V, then this means that there's a total of 3 times 1 equals 3 ways to get from U to V, with the intermediary step being I, right? And let's say there's no edge between I and V, so there's 0 ways. Well, then this would be 0. So we can get this. We can get the number of paths, K plus 1 length paths, going from U to V with I in the middle by just multiplying the number of ways to get from U to I and the number of ways to get from I to V. And actually, we know these numbers already, right? Because by the inductive hypothesis, we want to know how many ways are there to get from U to I in K steps. Well, that's given by A to the Kth if we take the U I element of that. And then we know the number of ways to get from I to V, also by the inductive hypothesis, in 1 step is just the entry, the ith, vth entry of A. And now, so now we have an equation, right, for how many ways to get from U to V in K plus 1 moves with I in the second to last position. And the way to get all of the paths then is just to consider the sum over all possible I, right? Because we just want to ask how many total paths are there is just the same thing as to ask how many paths are there that stop at like the first point on the second to last step, plus the number of ways to stop at the second point on the second to last step, et cetera, et cetera, et cetera. So we want to take the sum over all I here of this. And I claim that this actually just gives us A to the K plus 1, the UV entry of it. And we'll see that this is true. Because consider the matrices A to the K and the matrix A. Well, if we want to get the uth vth entry of A to the K plus 1, we'll just take the uth row of A to the K, say it's like this row, to visualize, and then the vth column of A, and take the dot product of that, and that will give us A to the K plus 1 uth vth entry. And that's exactly what this equation is doing right here, right? It's taking the uth row of A to the K and the vth column of A, and it's just dotting them together. So we see that this proves our inductive hypothesis. And this is a cool result because it gives a convenient way to calculate the number of K-length paths from one web page to another, from one node to another in a directed graph. And if we want to know all the paths that are at most K, then we could just add it up. We could add up like A plus A to the squared plus A to the third, et cetera, and then just take the uth vth element of that. Another thing that we could do is, let's say we're wondering, oh, what is the shortest path between U, V in this graph? Well, first we could check A, U, V, and then if there exists, if that's 1, well, then there's a way to get from it in one move. If that doesn't exist, then we go to a squared uv. And if that does exist, then 2 is the shortest path because this tells us there's no path of one length. And we just keep going up until we get a non-zero value. And when that changes, that indicates, well, that must be the shortest path because we checked everything shorter than it doesn't work. And so by assuming this data structure, by assuming the adjacency matrix, we're able to give some algorithms dependent on that data structure that tell us cool, important things about the graph. So this is just like a little sort of foray into data structures.